The next 14 minutes will show the tremendous difference that modern development techniques can give and how we can get there. Modern development claims to resolve whatever you find to be the most painful technical problem in your company. For example, some companies went from shipping thousands of bugs per year to less than 10. What was their secret? Doing unit tests well. So how do we create good unit tests? I get this question a lot. After all, some people have used unit testing and made code harder to refactor with tests that mostly find red herrings. Meanwhile, others have used unit tests with the opposite results. Their code became easier to refactor and tests found information. So what makes the difference? The difference comes from how devs choose test characteristics. While all developers are working on the same sets of characteristics, each assumes a different shade, a different personal bias, without really realizing that they're making a choice. As an example, let's explore assumptions about test execution time. Like most assumptions, this will give different results in code bases of different quality. Bob assumes his tests will run 2,000 times per second, fully in parallel. Since this is only possible with good quality code, Bob developed skill at refactoring any code into good quality code. Anytime that Bob tests code, he first refactors it to be high quality, then he tests it. Over time, he continually makes any code base better. Meanwhile, Charlie assumes his tests are going to run 10 times per second, basically one at a time. He develops skills using complex testing strategies that can handle even the worst code, such as mocks and dependency injection. His techniques always work, but they also make the code slightly harder to change, lowering its quality. Over time, he consistently makes any code base worse. Finally, Sally assumes that some things can be tested quickly and others require the slow approach. So when Sally finds reasonably good code, she'll refactor it and test it. But when she finds reasonably bad code, she adds test complexity. She improves code that is better than average and worsens code that is below average. Over time, her unit testing will tend to drive your code base towards an extreme. Because Sally represents the default assumption, good quality code bases teach developers to refactor, and then the code base gets better. Meanwhile, poor quality code bases tend to teach developers to use complex testing techniques, and the code base gets worse. When we also look at several other characteristics and the many assumptions under them, it becomes increasingly unlikely that your unit testing will handle a code base with even moderately poor quality. Yet, most of us slog every day through legacy. We would dream of working in even moderate quality code. So how can we hope to make unit testing work in our real world? The good news is that it's measurable. You can know how good your combination of assumptions is, creating solid unit tests. In essence, you're measuring test effectiveness. To understand this measure, let's look at where we apply our assumptions, which is every time a developer writes a test. When testing, developers apply their assumptions when they answer two fundamental questions. First, what exact changes should I make to my code to make it easy to test? And then second, how should I test the resulting code? Every developer asks and answers those questions. The difference between developers is the quality of their answers. Our test effectiveness measure guides you to high quality answers. The measure is basically how easy is it to write great tests? But let's make that a little more measurable. So easy means how few complications do I have to introduce? And great means tests that are simultaneously microtests and test as spec. However, what are these complications? And how do we define those two traits? Let's look at the testing complications first. Examples include using a mock, using a computer science term in a test, static data, shared resources, using your product code differently from the program's intent, and many, many more. Each complication makes your code base a little harder to change in the future. Therefore, answering the fundamental questions in ways that remove complications will lead to better code. Now let's look at what makes a great test. Great tests have two traits. First, they're microtests. Each test verifies one aspect of one behavior and executes nothing else. Second, they're tests as spec. Each test verifies a behavior that the customer cares about using their own language. Tests that meet both of these traits will provide great feedback throughout development. The best answers to two fundamental questions are ones that completely meet both of these traits at the same time. But of course, your code can't be tested this way. Right. In fact, most developers can't test their code this way unless they happen to be writing unit tests on clean code. Legacy code cannot be tested this way, at least as it is currently written. The only remaining option is to refactor the messy code. If you're shaking your head, I understand. Refactoring messy code is hard. But then, refactoring is also the only way unit testing gives value. The first attempt to write any test will fail. It'll show you that the code would require many complications, or we would have to fix a design flaw. We choose to refactor. The second cycle will be closer to testable, but there will still be flaws. Eventually, we will stop seeing complications and will actually write the test. Unit testing is a feedback loop informing you about your design quality. By refactoring where that design quality is low, you can then write the unit tests without complications. And the improved design quality is what actually gives you the benefits claimed by modern development. We see this in examples that will otherwise look like unrealistic one-off successes, such as when Medtronic automated their FDA approval process and were able to consistently get new pacemakers approved in only 8 days. Or when one developer at Facebook, during his first week on the job, not only shipped code, but generated $185,000 in incremental revenue. These aren't just one-off luck miracles, though. Each are a result of every developer listening to their feedback loop and refactoring dozens of times every day until success. We've covered the conceptual ideas, so now let's get into the details to start. The first action is simply to rethink the purpose of unit tests. The purpose of old-school manual unit tests was to validate whether your code was working. However, automated unit tests don't actually accomplish that very well. Instead, they're intended to define what your functionality should be and to give you feedback on the quality of your design. Now, that sounds a lot like the spec from 20 years ago. It defined design and requirements. But now that purpose is being accomplished by the test suite. Modern development still has a spec, but instead of one document written in advance, it's implemented as 10,000 microtests, each written just in time. Let's make a great spec. Regardless of the implementation, any spec must simultaneously have two qualities. First, a spec must be non-redundant so that its parts don't conflict. The microtest trait is defined to ensure that non-redundancy. Secondly, a spec must also communicate to a variety of audiences, including real users and developers. That is exactly the meaning of test as spec. Together, these two traits will make your tests effective as a spec. These traits also have a more important effect. They are opposing design forces that drive your code towards good design. If you can easily write tests that are microtests and test as specs, then your design must have small chunks with high cohesion that match customer value. If it's hard to write quality tests, then you have an emergent design rather than a cohesive design. Cohesive designs are easier to change than emergent designs. Changing a design with emergent behavior will simply generate more bugs. So designs that are easier to test will also result in fewer bugs being written over time. The tests don't find your mistakes. They guide you to create designs that produce fewer mistakes. Let's apply this in a real system. There are two cases. Sometimes you're writing a new method, and other times you're modifying existing methods. The best technique for new code is test-driven development. First, you write a little bit of a spec for the code you're about to write. Then you write some code that passes the spec. Then, this is the most important part. You try to write the next test, and you notice how easy it is. If it is easy, you continue. And the instant it becomes hard, you pause, reflect, and refactor. Existing code is both easier and harder because we already have a known good solution. We just don't know what it is. We don't know what the current code does, but we know it is serving the business's current needs. We need to record exactly what it does and then react accordingly. The best technique for existing code is read by refactoring. First, you look at the code and you learn one thing about it. Then you write that down. Sometimes you learn a fact about the existing code structure. You write those down as design improvements by refactoring. Other times, you'll see specific data examples or customer rules. You'll write these down as tests that become part of your spec. At some point, the spec describes enough of the system for today's story. Then we change the spec and finally change the code to meet the new spec. so we can create a great spec. And what's the point? I mean, what's the effect on the business? Well, many teams have virtually eliminated bugs. Nancy von Schoenfurt described one example team who built an embedded system across 2.5 years, and only 50 bugs ever created, and none ever found in production. Hunter did even better. In 6 years, they created only 3 bugs. Other teams chose to decrease time to market. Many products ship to production these days more than 1,000 times a day. But the analysts at Merrill Lynch did even better. The analysts found they could create a hypothesis, and then the software team created custom software to test and disprove those hypotheses in less than an hour. Medtronic leveraged their regulated environment to increase their speed when they automated FDA approval based on their tests and their commit log. So if this is all magical and good and has known implementations, why isn't it universal? Well, it turns out that there are 3 significant obstacles. The first obstacle is your existing integration test suite. Unless your code is already well designed, these tests are not microtests. Every code change to enable microspecs, and in fact every code change to your system as a whole, will require updating several of these tests. The way out of this obstacle is a technique called squeezing your tests. We wrote about that extensively early in our legacy code newsletter. The second obstacle is intertwined code. Every piece of code is locked to every other part of your system, so you can't isolate or microtest anything. Some techniques to explore in this space include Llewellyn-Falco's peel and slice and our TechNet newsletter articles on God classes. A third obstacle, regulatory approval. This actually isn't an obstacle, but your internal processes might be. Your company has developed processes, roles, and often entire departments just to respond to the risks created by the software development. Using microspecs will eliminate many of those risks and threatens those departments. These, of course, were quick responses to the obstacles. Please consider joining our Code by Refactoring Slack channel to discuss further, as well as subscribing to our monthly newsletter dedicated to solving legacy code problems in excruciating detail. Modern development is a huge topic. Even TDD and refactoring are large. Doing either well requires upgrading the software design skills of everyone on the team. Expertise will take time, but it is easy to start. Your next commit is either going to create entirely new code, or it is going to edit existing code. If it is new code, then write the spec first, and write it as a micros test. If it is existing code, then read the existing code by refactoring it. Extract out enough of the existing spec to clearly define all the behaviors for a small section of code you're going to alter. Or, if you're in a learning mode, then spend 1 hour as an ensemble or a pair. Either pick a new story and write all the microspecs for that story, or pick a 50-line existing method and use code by refactoring to extract the full spec. In the worst case, you will discover that you have more to learn. You'll abandon your commits and try again, but with more knowledge about the problem and more design skill. More likely, however, you will make your code a little better. You will learn a design pattern or a little way to think about program flow or naming. You'll apply the skill directly in the code, so the change may be small, but you'll start to see a little bit of the benefit. Expect easier communication among team members, process steps that you can simplify or eliminate, and designs that can change faster and with fewer bugs. These stories sound far-fetched and even impossible, but they are the norm among teams who choose to write microspecs and refactor every time those tests are not trivially easy to write. Coding in this way is also easier. The spec and the code are tiny, clear, they're fast to write. You check in with confidence. This lack of worry keeps your mind free to think strategically. Automated microspecs allow you to produce the same product with less mental effort. The only secret is to see every complication as the code asking you to refactor.